You've already built impressive customer support chatbots. You're clearly a wizard with prompt engineering, truly understanding how to get a single AI agent to perform incredibly well. But what if your AI agents could do more than just, follow those meticulously crafted instructions? What if they could actually talk to each other, forming a cohesive team? What if they could manage their own resources like a well-oiled machine, making smart, cost-effective decisions on the fly? And what if they could even think their way through incredibly complex, multifaceted problems, just like a high-performing human team, showing their work and even correcting their own mistakes? That's exactly where we're going today. From single, powerful agent solutions to building AI systems that can truly collaborate, reason, and adapt autonomously. It's a big step up. In this deep dive, we're unlocking the foundational concepts from the Agentic Design Patterns book. Our mission really is to give you a clear mental roadmap. We'll be breaking down the intricacies of interagent communication, resource-aware optimization, and advanced reasoning techniques. Think of this as your essential next step, equipping you to develop even more powerful, intelligent, and truly adaptive AI solutions.
And that's crucial because many of you listening are focused on applying your Python skills to make a profound difference, perhaps even in critical high-stakes areas like supporting domestic violence crisis response organizations. This deep dive is, I think, tailor-made to help you understand how these agentic patterns can transform your existing knowledge, transform it into systems that are not just smart, but truly resilient, efficient, and reliable. We're moving beyond individual chatbots that just answer queries, We're moving towards orchestrated AI solutions that can coordinate a multi-pronged response, systems that can maintain service continuity even under extreme pressure and reason through the nuanced complexities of real-world scenarios where, well, every decision matters.
Absolutely. Resilience and orchestration, those are key themes. We're going to unpack the what, why, and how of these patterns. We'll give you concrete examples, dive into a bit of code to see them in action, and always bring it back to how you can leverage this for truly impactful AI solutions. So what specific challenges are you hoping to overcome by taking your AI to this next level of autonomy and collaboration? Let's get started.
Yeah, okay, let's unpack this with our first major topic, interagent communication, or A2A. This is really all about enabling AI teams to talk to each other. We often build powerful individual AI agents, right? And they can be incredibly effective at specific, well-defined tasks. But what happens when the problem you're trying to solve gets really complex and multifaceted? Even the smartest single agent, no matter how well prompted, can, well, hit a wall.
That's right. And what's truly fascinating here, and what the source material highlights, is that the limitation isn't usually the individual agent's intelligence or its ability to process information. It's often its isolation. The source states, individual AI agents often face limitations when tackling complex, multifaceted problems. This isolation prevents the creation of sophisticated systems. It's like having a brilliant specialist who just can't communicate with anyone else on the team.
Right, a silo.
Exactly. And this raises an important question for developers like you. How do we get diverse AI agents maybe built with different frameworks by different teams or for different purposes? How do we get them to collaborate effectively and seamlessly? The answer precisely is interagent communication, or A2A.
Okay, A2A. And how does that connect back to, say, the crisis response goal?
Well, imagine an AI system designed for a domestic violence crisis. A single chatbot might tell a survivor where the nearest shelter is. That's useful, but limited. But a collaborative system could have one agent quickly assessing immediate risk based on a survivor's words, while another simultaneously gathers real-time information about local shelter availability. And maybe a third connects with legal aid resources, and a fourth handles secure, encrypted communication with a human advocate or schedules follow-up check-ins. Without a common language, a shared protocol for these specialists to communicate, they're just disparate, powerful tools operating in silos. They can't coordinate. A2A offers that common language, that connective tissue, allowing them to truly function as a coordinated unit. It's like orchestrating a high-performing emergency response team, but, with AI.
That's a powerful vision of interoperability, but I can't help but wonder about the practicalities. If you're coordinating agents built by different teams, maybe even in different companies, what are the biggest hurdles to achieving that seamless communication, and how does A2A specifically overcome them?
That's an excellent question, yeah. And it really gets to the core why A2A is so revolutionary, or potentially revolutionary. The real aha of A2A isn't just that agents can talk, but that it forces a certain modularity and self-description, like the agent card we'll discuss, that fundamentally scales future AI development. Think of it as building the Internet Protocol for AI agents before the Internet of AI agents even fully exists. It's laying that foundational layer. So A2A is an open standard. It's designed specifically to facilitate universal communication between AI agents, ensuring true interoperability. This means agents developed with entirely different frameworks, whether that's LangGraph, Crew AI, or Google ADK, they can all work together seamlessly.
So it's like everyone agreeing to speak the same basic language,
Yeah.
even if they have different accents or dialects.
Precisely. It removes that fundamental barrier.
And this isn't just a theoretical concept, is it? It sounds like there's significant industry backing.
Absolutely. This isn't just academic. If we connect this to the bigger picture, A2A is backed by major players across the tech landscape. We're talking names like Atlassian, Box, LangChain, MongoDB, Salesforce, SAP, ServiceNow, big names. And even more tellingly, Microsoft is planning integration into Azure AI Foundry and Copilot Studio. This broad support really signals its immense importance as an evolving open source protocol. It's about fostering interoperability and innovation across the whole AI ecosystem. Fundamentally, it's an HTTP-based protocol. It leverages familiar web standards, specifically JSON RPC 2.0, for seamless coordination, task delegation, and information exchange between these AI entities.
JSON RPC 2.0. Can you unpack that just a tiny bit?
Yeah.
Why that specifically?
Sure. Think of JSON RPC 2.0 as a lightweight, standardized way to package up remote procedure calls, basically, requests for another system to do something, and their results using JSON. Because it uses JSON and HTTP, it's incredibly easy for different systems, even those built in totally different programming languages, to communicate over the web. It's simple, widely understood, and efficient for this kind of interaction.
Okay, makes sense. Simple and standard. Now that we understand the broad strokes, let's dive deeper into the core concepts of A2A. These are the fundamental building blocks of how this collaboration actually happens. First, let's talk about the core actors involved. Every interaction revolves around three main entities, right? There's the user, which is, well, you or anyone initiating a request for agent assistance. Then there's the A2A client. This is an application or an AI agent itself that acts on the user's behalf to request actions or information from another agent. And finally, you have the A2A server. This is a remote AI agent or system that provides an HTTP endpoint to process these client requests and send back results.
Exactly. And the opaque nature of the A2A server is a really critical design choice here.
Opaque.
Meaning the client doesn't need to know or care about the server's internal operational details, how it processes information, which specific LLM it uses, its internal code structure. None of that matters to the client. All the client needs is the A2A interface. This promotes modularity. It allows each agent to be developed, updated, and even swapped out independently, as long as it adheres to the A2A protocol for its external interface.
Okay, so you can upgrade the server agent without breaking the client agent, as long as the contract, the A2A interface, stays the same.
Precisely. This decoupling is absolutely key for building truly scalable and maintainable multi-agent systems. You avoid tight dependencies.
Okay, this next piece sounds fascinating, especially for how agents discover each other. The agent card. So each agent has an agent card, typically a JSON file. You described it as like a digital passport or maybe a LinkedIn profile for the AI.
Yeah, that's a good analogy, except it's always up to date and hopefully brutally honest about its skills.
All right, so it contains its name, a clear description of what it actually does, its endpoint URL so other agents know where to find it online, its version number, and then crucial details like supported capabilities. Does it do streaming, push notifications, and its specific skills, default MP output modes, and any authentication requirements. It's quite detailed.
That agent card is absolutely essential. It's the cornerstone for discovery and interaction. The example of the WeatherBot agent card from the source material illustrates this perfectly. It shows how capabilities like streaming, true, are declared. And specific skills like get current weather and get forecast are explicitly declared, often with descriptions and even examples of how to call them.
So it's like API documentation, but standardized for agents.
Exactly. Now think about a crisis response system. Imagine an agent card for a resource locator agent. This card would clearly define exactly what it can do. Maybe find nearby shelters with availability, list legal aid services for specific issues, provide emergency transportation options. It would also specify its authentication needs. Maybe it needs a specific token to prove the request is coming from a trusted part of the system. This formal declaration makes it incredibly easy for other agents, say a crisis intake agent or a safety planning agent, to discover it and immediately leverage its services without needing any prior hard-coded knowledge of its internal workings. It's the blueprint for dynamic collaboration.
That agent card is essential, but it only works if other agents can find it, right? You can't use the service if you don't know it exists or where it is. What are the common strategies for agent discovery in a dynamic system like this?
Good point. Discovery is key. The source outlines several practical strategies. One is using a well-known URI. This is a standardized web path, often something like well-known-agent.json, where an agent can publicly host its card. This makes it broadly discoverable, often automatically.
Kind of like robots.txt for websites, but for agents.
Sort of, yeah, in the sense of a standardized location. Then there are curated registries. Think of these as centralized catalogs or directories where agent cards are published and can be queried. These are really well suited for enterprise environments or maybe consortia where you need centralized management, vetting, and access control, especially for sensitive internal agents.
Like an internal app store for agents.
Pretty much. And finally, there's direct configuration. This is the simplest. Agent card information is just embedded directly in the client agent's code or configuration or shared privately. This works fine for closely coupled systems or private setups where dynamic discovery isn't as crucial. But regardless of the method you choose, securing those agent card endpoints is absolutely vital, especially if they contain any sensitive, though hopefully not secret, information.
How do you secure them? What are the options?
Standard web security practices apply. Robust access control is a must. You might use IP restrictions, authentication tokens, or for really strong security, mutual TLS, MTLS.
Okay, you mentioned MTLS before. Can you elaborate a bit more on that? For those maybe less familiar with networking specifics, what does that really mean in practice for security between agents?
Certainly. Mutual TLS, or MTLS, is a significantly robust security measure because it provides two-way authentication. Normally, when your browser connects to a secure website, HTTPS, your browser verifies the website's identity using its certificate. That's one-way TLS. With MTLS, it goes both ways. Not only does the client agent verify the server agent's identity, but crucially, the server agent also verifies the client agent's identity. Both sides present a valid cryptographic certificate to prove who they are. This ensures that only authorized agents can talk to each other.
So it's like both agents showing their ID badges before they start talking.
Exactly. It creates a secure, encrypted tunnel where both participants are verified. It's an incredibly strong guarantee of identity and privacy, which is essential for sensitive data exchanges. Think about the crisis response scenario. You absolutely need to be sure that the agent requesting shelter information is legitimate and authorized, and that the communication channel is secure. This really raises important design questions about building trust and ensuring verifiable access in a multi-agent environment, especially when dealing with highly sensitive information.
Makes sense. Trust but verify, built right into the connection. Okay, so agents can find each other, authenticate securely. Now, the real work begins. How is the actual flow of work, the communications and tasks, structured within A2A to manage these potentially complex, long-running processes?
Right, the workflow. It's structured around asynchronous tasks. These are the fundamental units of work, especially for processes that might take a while. Each task gets a unique identifier, like a tracking number, and it moves through a series of well-defined states, like submitted, working, completed, or maybe failed. This asynchronous design is really clever because it inherently supports parallel processing. Multiple agents can work on different parts of a larger problem simultaneously without blocking each other.
So one agent doesn't have to wait for another to finish before starting its own piece.
Exactly. Now, the actual communication between agents happens through message. A message itself has two main parts. It contains attributes, which are essentially key value metadata describing the message, things like its priority, maybe a timestamp, or related IDs. And it also has one or more parts, which carry the actual content being delivered. This could be plain text, binary data-like files, or structured JSON.
And the outputs, what the agent produces.
The tangible outputs generated by an agent during a task are called artifacts. Like messages, artifacts are also composed of one or more parts. And importantly, artifacts can often be streamed incrementally. So if an agent is generating a long report, it can start sending chunks of it back as they become available, rather than making the client wait for the whole thing. Very useful for responsiveness.
Okay, and how do you keep track of related tasks? If one agent asks another agent to do something, and that agent asks a third, how does the system know these are all part of the same original request?
Good question. That's where the context data comes in. It's typically generated by the server agent and passed along. This context acts like a thread identifier, grouping related tasks together and preserving the context across multiple asynchronous interactions. It ensures that even though tasks might be happening in parallel and asynchronously, the overall conversation or workflow remains coherent.
Got it. So async tasks, messages with attributes and parts, artifacts for outputs, and context IDs to tie it all together. Now, A2A also supports various interaction mechanisms, different ways for agents to talk. Instead of just listing them, could you highlight the core distinctions and maybe tell us when a developer would choose one over another?
Absolutely. The fundamental distinction, as you might guess, is between synchronous and asynchronous communication. For synchronous request response, it's simple. The client sends a request and just waits, blocks until it gets a complete response.
When would you use that?
It's ideal for quick, immediate operations where you need an answer right away and the answer comes back fast, like checking a single fact, looking up a status, something that takes milliseconds or maybe a second. But for longer tasks, that synchronous wait becomes impractical. That's where asynchronous polling comes in. Here, the client sends a request, gets an immediate, okay, I'm working on it back, along with that unique task ID we talked about. The client is then free to do other things. Periodically, it polls the server using the task ID, asking, are you done yet, until the task is complete.
So good for tasks that might take several seconds or even minutes, like generating a report or running a complex analysis.
Exactly. It avoids tying up the client. Now, beyond polling for real-time incremental results, there's streaming updates using server-sent events, or SSE. SSE establishes a persistent one-way connection from the server back to the client. The server can then continuously push updates as they happen.
Like live progress updates on a long task or a continuous feed of data.
Perfect examples. Think stock tickers, live log streams, or maybe the status of a complex multi-step process. And finally, for very long-running or maybe resource-intensive tasks, things that could take minutes or even hours, there are push notifications via webhooks. In this model, the client registers a callback URL with the server when it submits the task. The server then simply sends an asynchronous notification, a webhook call, to that URL when the task status changes significantly, like when it's completed or if it fails.
So the client doesn't have to keep asking. The server just tells it when something happens.
Right. It eliminates the need for constant polling, which can be inefficient for very long tasks. What's really important here, tying back to the agent card, is that the card specifies whether an agent supports capabilities like streaming or push notifications, so the client knows which interaction styles are available. And critically, A2A is designed to be modality agnostic.
Modality agnostic, meaning
It means it works for any type of data text, audio, video, images, structured data, whatever. The protocol itself doesn't care about the content type of the message parts or artifacts.
that's huge for flexibility.
It is, especially for something like a domestic violence crisis system. An immediate safety assessment might use a quick, synchronous request response.
Aye.
Processing complex legal information for a survivor, that could easily be an asynchronous polling task. Receiving real-time updates on available shelter capacity across multiple locations, that would definitely leverage streaming. And the modality agnosticism means the system could potentially process secure voice calls, transcripts, or even video input from a trusted source, allowing for a much richer and more responsive interaction with the survivor.
Okay, that makes a lot of sense.
Right.
Different tools for different jobs. Now, with sensitive applications like crisis response, security isn't just a feature, it's absolutely non-negotiable. How is security baked into A2A?
Security is absolutely built in, and it has to be. It covers several critical aspects. Mutual TLS, MTLS, as we just discussed, ensures encrypted and authenticated connections, preventing unauthorized eavesdropping or agent impersonation. Comprehensive audit logs are usually recommended or required. These meticulously record all inter-agent communications who requested what, when, what the response was. This provides a verifiable trail for accountability, debugging, and security analysis. The agent card declaration itself plays a role. It explicitly states the authentication requirements for interacting with the agent, making security policies clear and discoverable. And credential handling typically uses secure standard methods like OAuth 2.0 bearer tokens or API keys passed securely via HTTP headers. You definitely don't want credentials exposed in URLs or message bodies. The emphasis on these robust security mechanisms isn't just, good practice. It's non-negotiable for ensuring the integrity and confidentiality of inter-agent data exchange, especially in critical applications where privacy and data protection are paramount.
Right, you can't afford leaks or unauthorized access there. Now, the source also clarifies that A2A isn't the only protocol in this space. It complements Anthropic's Model Context Protocol, or MCP. There's a helpful diagram, figure 1 in the source, that visually compares them. What's the key distinction, and why might we need both?
That's a great point to clarify. They serve different but related purposes. If we connect this to the bigger picture, A2A fundamentally focuses on agent-to-agent coordination and task delegation. It's about enabling collaboration between different AI entities, allowing them to communicate effectively and share work amongst themselves. Think of it as the internal communication network for an AI team.
Okay, A2A is agent to agent. What about MCP?
MCP, on the other hand, is primarily about structuring the context that an agent needs to interact effectively with external data and tools. Think browsers, file systems, vector databases, external APIs, code interpreters. MCP helps package the information the agent needs to use these tools and understand their outputs.
So A2A helps agents talk to each other, while MCP helps agents talk to the outside world and its tools.
You've got it. They address different but equally vital aspects of building a complete agentic system. A2A enhances the efficiency and interoperability among the agents themselves. MCP gives those agents the ability to perceive and act upon the external world through tools. Together, they form a powerful combination. Agents can coordinate internally using A2A, and they can interact effectively with external resources using MCP.
That makes sense. You need both internal team communication and ways to interact with the outside world. So what does this all mean for real-world applications and use cases? How does A2A translate into actually building these sophisticated AI solutions?
Well, A2A is truly indispensable for the kinds of sophisticated systems we're talking about. We're talking about enabling multi-framework collaboration. As we mentioned, different agents, perhaps built with different technologies like Google ADK, LangChain, or Crew AI, can all work together harmoniously because they speak the common A2A language. It's also key for automated workflow orchestration. A2A enables agents to seamlessly delegate tasks in complex sequences. For example, one agent might collect raw data, delegate to an analysis agent, which then delegates to a report generation agent. And finally, it's crucial for dynamic information retrieval. Agents can request real-time information from specialized data fetching agents. Maybe one agent is an expert at querying a specific database, another at scraping a particular website, ensuring access to the most current data without every agent needing to know how to fetch everything.
Okay, let's bring that back to the listener's goal, the domestic violence crisis system. How would A2A enable that multi-framework orchestrated approach?
Right. Imagine a sophisticated system. An intake agent, maybe built using LangGraph for its state management capabilities, could quickly identify urgent needs from an initial conversation with a survivor. It could then seamlessly delegate, using A2A, to a resource agent. This agent might be built in Google ADK because it needs robust connections to external APIs for real-time shelter availability, local legal aid service lookups, or transportation options. In parallel, the intake agent might delegate to a follow-up agent, perhaps developed with Crew AI for managing role-based interactions, to schedule check-ins or provide ongoing tailored support resources. A2A is precisely what makes this multi-framework orchestration possible. It ensures that the survivor receives comprehensive and coordinated support from a system that acts as a single intelligent entity rather than just a collection of disconnected tools. Each specialist agent contributes its expertise through a common communication protocol.
That really paints a clear picture of how these components could work together. Now let's dive into some code to see this in action. The source gives us Python examples from the Google A2A samples repository, focusing on an ADK-based calendar agent. How does this illustrate the A2A compliance we've been discussing?
This code is a great practical example, yeah. It shows the architectural thinking. The create agent function shows an Elm agent being constructed. It's given a specific tool set, the calendar toolset, for Google Calendar API access. Now, this isn't just about defining an agent in isolation. It's about giving it a specific set of capabilities and instructions for its intended role, in this case, interacting with calendars. It defines the agent's underlying model, like Gemini 1.5/001, its name, description, and crucially, its dynamic instruction that even includes the current date, giving it necessary temporal context for scheduling.
Okay, so that sets up the agent's core logic.
Yeah.
But how does it become A2A compliant? Where does the communication protocol come in?
Right, that happens in the main function setup. This is where we truly transform our specialized AI agent into an A2A compliant web service. It's not just about listing its capabilities internally, it's about formally declaring them in an agent card, which acts like a public API contract, and then wrapping the agent in a web server so other agents can discover and interact with it without needing to know anything about its internal Python magic.
No.
So first, it verifies API keys, handles authentication setup, then it defines an agent's skill, like check availability, making its specific capabilities explicit and machine-readable. Next, it constructs that all-important agent card. This includes the agent's name, description, the URL where it can be reached, its version, default I/O modes, and its declared capabilities like maybe streaming, true if it supports streaming results.
So the agent card is built programmatically based on the agent's configuration.
Exactly. Then the ADP agent executor integrates the underlying ad agent, the one with the calendar toolset, with this agent card. It uses some in-memory services here for managing artifacts, sessions, and memory state for the agent. Finally, a Starlet web application is created. Starlet is a lightweight ASGI framework, great for building async web services in Python. This web app incorporates an authentication callback to check credentials and, crucially, the A2A Starlet application from the ADK library. This component takes the configured agent and its agent card and exposes the necessary A2A HTTP endpoints using Uvicorn as the server.
Wow. So that whole process turns your Python agent code into a standardized, discoverable, interoperable web service ready for the multi-agent ecosystem.
That's the goal. This practical approach truly shows how agent cards and frameworks like ADK enable developers to build these interoperable AI agents. It's about designing for the network from the start.
And connecting this back again, how could a developer adapt this calendar example for the crisis response system?
Well, you could adapt this exact pattern to create a scheduling agent within that system. This agent wouldn't manage personal calendars, but maybe shared resources or appointments. It could use an authenticated Google Calendar API or maybe a different scheduling API wrapped in an ADK toolset. Its job would be to help human crisis responders manage appointments, schedule crucial follow-up sessions for survivors, coordinate multi-agency meetings, or track resource availability slots. Its capabilities, like check responder availability or book survivor follow-up, would be clearly defined in its A2A agent card. Other agents in the system, perhaps an intake agent identifying a need for follow-up or a case management agent coordinating services, could then easily discover the schedule agent via its card and securely interact with it using A2A calls. They could query availability or book those crucial follow-up sessions, all without needing to understand the messy details of the underlying scheduling API. This means your human staff are freed up for direct, high-touch support, while the AI handles the complex, collaborative logistics behind the scenes.
That's a really tangible benefit, automating the coordination overhead. Okay, this next section is where things get really interesting, I think. We've talked about agents talking to each other. Now let's talk about agents thinking smartly about their resources. This section is on resource-aware optimization, or basically how to make your AI a smart spender. LLM-based applications, as you probably know all too well, can be both expensive in terms of API calls or compute, and sometimes slow if not managed carefully. So how do you decide, for example, between a super accurate but pricey model like GPT-4 or Claude 3 Opus and maybe a faster, cheaper one like Gemini Flash or GPT-4 or Mini for a specific task? That's the core challenge, right? Resource-aware optimization. It's about more than just planning what actions to take. It's about making smart, dynamic decisions on how to execute those actions within predefined budgets, whether those budgets are financial cost, time limits, latency, or computational power.
Absolutely. And this really differs from simple task planning because it involves dynamic monitoring and management of these various resources: computational, temporal, financial. Consider an agent tasked with analyzing a large data set. If a preliminary report is needed immediately for, say, an agent briefing, it might intelligently choose to use a faster, more affordable model, like Flash, to summarize key trends quickly. Get something useful out fast. However, if a highly accurate financial forecast is required for a critical investment decision, and there's a larger budget allocated and more time available, the agent would dynamically allocate more resources. It would invoke a powerful, maybe slower, but more precise predictive model to ensure the highest quality result.
So the agent itself makes the trade-off decision based on context and constraints.
Ideally, yes. And a critical strategy in this category, highlighted clearly in the source, is the use of fallback mechanisms. The critical insight here isn't just about saving money, although that's often a benefit. It's really about building unshakable resilience into your AI systems.
Resilience, meaning it keeps working even when things go wrong.
Precisely. It's realizing that often getting a good enough answer through a fallback mechanism is vastly superior to total system failure, especially when, lives might depend on continuous operations. So if a preferred, perhaps more advanced or specialized model is overloaded, or maybe it gets throttled by the API provider, or it's just temporarily unavailable, the system automatically switches to a predefined default or maybe a more affordable, readily available alternative model. This ensures graceful degradation of service and continuity, preventing complete system failure. It's absolutely essential for reliability in high-stakes environments.
And bringing this back to the mission-focused domestic violence crisis response, that resilience is paramount.
It's non-negotiable. In that context, an AI system needs to be incredibly resilient. If the most advanced, nuanced sentiment analysis model, the one that's best at detecting subtle distress cues, is overloaded or unavailable due to, say, a sudden surge in demand, a simpler but still effective sentiment analysis model should automatically step in. This ensures that no incoming message from a survivor goes unanalyzed, even if the initial analysis is less nuanced. It guarantees continuous support and prevents any critical communication from falling through the cracks, which could have devastating implications for a survivor's safety. It's about ensuring a minimum viable yet critical service is always available, no matter what.
That makes perfect sense. Okay, so fallback is key for resilience. What are some other practical applications? Where else can resource-aware optimization make a big difference for developers building these systems?
Oh, it's crucial across the board for building practical, deployable AI we're talking about. Cost-optimized LLM usage. Simply choosing the right-sized, right-priced LLM for the specific task at hand, not using a sledgehammer to crack a nut. Latency-sensitive operations, ensuring real-time or near-real-time responses by dynamically picking faster reasoning paths or models when speed is critical. Energy efficiency. This is becoming more important, especially for agents deployed on edge devices, maybe in mobile crisis units or low-power settings. Choosing less computationally intensive models saves battery. Fallback for service reliability. As we just discussed, absolutely crucial for continuity and robustness. Data usage management. Optimizing how much data is processed or transferred, maybe by summarizing context or using models with smaller context windows, saving bandwidth or storage costs, and even adaptive task allocation in multi-agent systems. Agents could potentially self-assign tasks based on their current computational load or available time budgets, optimizing the whole team's throughput.
That's a pretty broad range of benefits. How would this look in that crisis hotline AI example?
Right. For a crisis hotline AI, this translates directly into intelligent resource allocation and action. For a simple, factual query like, what is the phone number for X shelter? The system should immediately route that to a cheap, fast model like Gemini Flash, or maybe in a simple database lookup. Get an instant, low-cost answer. But for a complex emotional assessment or a situation requiring deep reasoning based on interpreting internal policies or safety protocols, it would recognize the complexity and utilize a more powerful, potentially slower, but absolutely essential model, maybe Claude 3 Sonnet or GPT-4, to ensure accuracy, empathy, and safety. And crucially, if that high-demand, powerful model is temporarily unavailable, maybe the API is down or rate limited, a fallback mechanism ensures basic but continuous support. Perhaps it reroutes to the simpler model for a basic response, or maybe it intelligently flags the interaction for immediate human intervention, but it never leaves the user hanging without any response.
So it's balancing efficiency for simple stuff with robustness and quality for complex critical interactions, plus having that safety net.
Exactly. It allows for both operational efficiency and robust, uninterrupted service.
Let's look at how this plays out in code. The source gives an example using Google's ADK. How can we implement this dynamic decision-making, this routing logic?
The source code illustrates the core components needed. First, it shows defining two distinct agents, each configured with different underlying models. There's a Gemini Pro agent designated for complex queries, explicitly configured to use Gemini 1.5 Pro or a similar powerful model. And there's a Gemini Flash agent for simpler queries, leveraging the faster, cheaper Gemini 1.5 Flash. This highlights the directability within ADK and similar frameworks to plug and play different models. You can even integrate models from other providers using something like LeetL-M as a bridge. This foundational step gives you the choice that resource-aware optimization needs to make.
Okay, so you have the different model options available as agents. How does this system choose between them?
That's where the query router agent comes in. The source provides a conceptual Python structure for this. This agent acts as the decision engine. The example shows a very simple routing metric, query length. Short queries go to Flash, long queries go to Pro. Now, that's obviously simplistic for real-world use.
Right. Query length doesn't always equal complexity.
Exactly. More sophisticated routers would be needed. You could actually use another LLM, maybe a cheap, fast one, specifically to analyze the incoming query's nuance, intent, and complexity. Or you could use traditional machine learning classification models trained to predict query complexity. This query router agent's job is to make that intelligent routing decision based on a deeper understanding of the query, directing it to the most appropriate downstream agent, Pro or Flash in this case. This dynamic routing capability is the heart of resource optimization here, balancing response quality with cost effectiveness.
Okay, so the router agent makes the call. But how do you know if the router is making good calls? How do you refine its logic?
That's where the critique agent comes in, playing a crucial, though maybe indirect, role in the optimization loop. The source defines a critic system prompt for this agent, positioning it as the quality assurance arm of the system. Its duties are defined as assessing findings, identifying missing information, raising critical questions about the reasoning or output, and offering constructive suggestions for improvement. Now, the critique agent doesn't directly manage the budget or make the routing decisions itself, but it indirectly contributes to resource-aware optimization by providing invaluable feedback on the outcomes of those decisions. Well, imagine the router mistakenly sends a really complex, nuanced query to the cheaper Flash model. The critic agent, upon reviewing the potentially shallow or inaccurate response generated by Flash, would flag it as suboptimal. This answer lacks depth, or this doesn't address the core complexity. Conversely, if a very simple factual query was unnecessarily sent to the expensive Pro model, the critic might flag that as potentially wasteful, assuming the cheaper model could have handled it. This feedback loop, whether automated or reviewed by humans, is essential for refining the router's logic over time. It helps you tune the routing criteria, leading to better resource allocation, improved overall quality, and ultimately significant cost savings.
So the router makes the call, the worker agent does the job, and the critic agent checks the work, providing feedback to improve the router's future decisions. It's like a little internal performance review cycle.
Exactly. It's about ensuring we're not just making decisions, but making good decisions with our resources and having a mechanism to continuously improve that decision-making process.
That's a powerful internal audit mechanism built right in. Now, the source also provides a full Python code example using OpenAI this time, demonstrating a more complete resource-aware optimization strategy through prompt classification and routing. This one's under an MIT license, courtesy of Mahtab Syed. How does this system intelligently direct queries?
Yeah, this is a fantastic, concrete example of a complete system that implements this smart resource management. Let's walk through it. The initial setup is standard. Load necessary API keys, OpenAI for the models, maybe Google custom search for real-time info, then initialize the OpenAI client. The core logic really begins with the classify prompt function. This function cleverly uses a powerful model like GPT-4o, though you could potentially use a smaller one, with a meticulously crafted system message. Its sole job is to classify the incoming user prompt into one of three predefined categories: simple, reasoning, or internet search. This classification is the crucial first step in the intelligent routing pipeline. It determines the most appropriate and cost-effective processing pathway before any heavy lifting or expensive generation begins.
So it uses an LLM to figure out what kind of question it is first.
Exactly. Then, if the classification comes back as internet search, the Google search function is triggered. This function performs a Google custom search using the user's query to get current, real-time information from the web. This is vital for ensuring the AI doesn't rely solely on its potentially outdated training data for things like current events, recent policy changes, or rapidly changing facts like, say, shelter availability.
Grounding the response in current reality. Makes sense. What happens next?
Following the classification and potential search, the generate response function takes over. This function intelligently selects the appropriate OpenAI model based on the classification. It might leverage a model like GPT-4 Mini for simple and reasoning classifications, typically faster and cheaper. However, if the classification was internet search, it switches to the more powerful GPT-4o. And crucially, when it calls GPT-4o for an internet search query, it injects the search results obtained earlier directly into the prompt context. This ensures the model's final response is grounded in that up-to-date information.
So the choice of model and the context provided depend on that initial classification.
Precisely. Finally, the handle prompt function acts as the orchestrator for this entire workflow. It calls classify prompt, then Google search if needed, then generate response. It then returns not just the final answer, but also the classification result and the specific model that was ultimately used. This provides transparent insight into the system's decision-making process, which is great for debugging and monitoring.
This really is a fantastic complete system example. It efficiently directs different query types to optimize methods. Different models, maybe with or without web search, to get the best possible response, balancing both quality and cost. For developers listening, it shows a clear blueprint for building this kind of intelligent routing.
And you could directly apply this pattern to classify incoming messages from survivors in a crisis response organization. A message could be classified as simple if it's a basic information request. What's the address for shelter Y? Handle with GPT-4 Mini. It could be reasoning for complex scenarios needing policy interpretation or multi-step advice. My ex is violating the restraining order. What are my options? Maybe still GPT-4 Mini if it's well prompted, or perhaps route to GPT-4 if high accuracy is paramount. Or internet search if it's about finding the most up-to-date local resource availability. Are there any legal aid clinics open near me today? Use GPT-4 with the search results. This classification ensures that the most appropriate and most cost-efficient model handles each query type. It optimizes both response speed and budget for potentially high-volume support, all without compromising on the quality of these critical interactions.
That's incredibly practical. Now, another powerful tool mentioned for resource optimization, especially if you want access to a wide range of models from different providers without juggling tons of API keys, is OpenRider. The source mentions it acts as a unified interface. How does it help developers manage model choice and reliability?
OpenRouter is really neat for simplifying access and adding robustness. It acts as a single gateway. The code snippet in the source shows a simple requests.post call to OpenRouter's chat completions endpoint. Notice how you can specify the model you want, like OpenRouter's 4.0, but you interact with the OpenRouter API endpoint and use your single OpenRouter API key. It abstracts away the complexity of dealing with multiple vendor-specific APIs and billing.
So one API key to rule them all, basically.
Pretty much, for a huge range of models. But it offers even more sophisticated features for optimization. One is automated model selection. You can actually specify a special model identifier like OpenRouter Auto. If you use this, OpenRouter itself will intelligently route your request to what it determines is an optimized model, chosen based on the content of your prompt and current model performance availability metrics they track. The specific model that was ultimately used is then returned in the response metadata, so you still have transparency.
Wow, so it can even try to pick the best model for you automatically.
Yes, based on their internal logic. And perhaps even more crucial for reliability is its support for sequential model fallback. This is super useful. You can provide OpenRouter with a prioritized list of models in your API call. For example, you might list Anthropic Claude, 3.5 Sonnet, Google Gemini Pro, Griffin Mythomax L2-13B. OpenRouter will first try to send your request to the primary choice, Claude 3.5 Sonnet in this case. If that fails for any reason, maybe Anthropic's API is down, you hit a rate limit, the model flags the content, OpenRouter automatically catches the failure and retries the exact same request with the next model in your list, Gemini Pro. It continues down the list until one of the models successfully processes the request or the list is exhausted.
That's huge for maintaining service continuity. It builds the fallback logic right into the API call.
Exactly, especially when you can't afford any downtime, like in a crisis support scenario. The cost and the model identifier returned in the response will then reflect the model that finally succeeded. They also provide leaderboards and access metrics to help you choose models.
So OpenRouter really provides incredible flexibility, unified access, and automated failover. It's like having a built-in load balancer and emergency backup system for your LLM calls, all through one interface.
It's a very powerful abstraction layer, yeah. But remember, resource-aware optimization actually goes well beyond just dynamically switching between different LLM models. The source outlines several other critical techniques that offer a really rich toolkit for developers looking to build efficient systems.
Like what else?
Well, for instance, there's adaptive tool use and selection. This isn't just about picking an LLM, but about the agent intelligently choosing the most appropriate and efficient tool, like a specific API call, a database query, a code execution, for each subtask it needs to perform, considering factors like API cost for that tool, its typical latency, and the quality of its results. Then there's contextual pruning and summarization. This focuses on minimizing the number of tokens sent in the prompt, which directly impacts cost and latency. Techniques include summarizing previous turns of conversation, extracting only relevant entities, or using more concise representations of information.
Keeping the prompt lean and mean.
Exactly. There's also proactive resource prediction, which involves trying to forecast future workloads or resource demands to preemptively scale resources or adjust strategies to prevent bottlenecks before they occur. In multi-agent systems, cost-sensitive exploration becomes important. Agents need to consider not just the computational costs of their own actions, but also the communication costs, like A2A message costs or latency involved in collaborating with other agents.
The overhead of teamwork.
Right. And then there are areas like energy-efficient deployment for power-limited environments, thinking about parallelization and distributed computing awareness to leverage multiple machines effectively, training learned resource allocation policies where agents actually adapt their resource optimization strategies over time based on experience. And of course, those graceful degradation and fallback mechanisms we discussed earlier, ensuring the system maintains core functionality even under severe resource constraints.
Wow, that's a much broader perspective. So what does this all mean? It sounds like resource optimization isn't just a single trick, but a truly holistic approach, a whole design philosophy for building AI systems that work efficiently and effectively in the real world.
That's a perfect way to put it. It's a comprehensive design philosophy. It's about acknowledging that resources, time, money, compute, energy, data are always finite and building systems that make intelligent trade-offs constantly.
And for the domestic violence crisis response AI, how might some of those other techniques apply?
Well, imagine an adaptive tool use agent. When a user asks for specific legal information, it might choose between doing a quick search in a local cached database of FAQs, very low cost, very fast, or making a more comprehensive but slower and potentially costly external API call to a specialized legal research service. The choice would depend on the perceived urgency and required depth of the query. Contextual pruning would be vital for managing long conversations while maintaining privacy. Instead of sending the entire chat history in every prompt, the system could summarize key points or extract only the immediately relevant safety information, reducing token usage and ensuring sensitive details aren't unnecessarily reprocessed. And graceful degradation ensures that even if, say, the advanced legal analysis tool is temporarily unavailable, the system can still perform its core functions like providing emergency contact numbers, basic safety tips, or connecting the user to a human advocate immediately. The system keeps working, prioritizing the survivor's immediate needs above all else, even when operating under constraints. These optimizations ensure the system is always performing its best possible function within the real-world limits it faces.
Okay, let's shift gears now. We've covered agents talking A2A and agents spending smartly, resource optimization. Now let's turn our attention to how agents can actually think deeper. This section is all about advanced reasoning techniques, because complex problems, especially in sensitive areas, demand more than just simple, sequential operations from AI. We need agents that can break down problems, consider intermediate steps, evaluate options, and reach robust, accurate conclusions. This means making the agent's internal reasoning process explicit, allowing it to truly show its work, so to speak, rather than just spitting out an answer.
Absolutely. And the core principle underlying many of these advanced reasoning techniques is the deliberate allocation of increased computational resources during inference.
During inference. So when the agent is actually generating the response, not during training.
Exactly. This doesn't necessarily mean you need a bigger GPU, but rather giving the agent more processing time or allowing it to take more internal computational steps for a single query. This extended thinking budget allows it to explore multiple potential solution paths, engage in iterative refinement of its own outputs, critically evaluate intermediate steps, or utilize external tools more effectively within its reasoning process. This significantly enhances accuracy and robustness, especially for complex problems that require deeper analysis, planning, and deliberation, where a quick, superficial answer just won't cut it.
Where do we see this being applied?
The source outlines diverse practical applications where this deeper reasoning is crucial. Complex question answering that requires synthesizing info from multiple sources, mathematical problem solving, sophisticated code debugging and generation, often involving self-correction, strategic planning like in games or business scenarios, often using techniques like React, medical diagnosis support, and complex legal analysis. These are all fields where deep, multi-step reasoning is absolutely paramount because the cost of error, well, it can be incredibly high.
And for our listeners focused on domestic violence crisis response, how does this deeper reasoning translate?
In that critical context, this could mean an agent capable of analyzing complex legal precedents relevant to a specific survivor's protection order case, or strategizing a long-term safety plan that considers numerous factors, dependencies, and potential outcomes. It could even mean an agent debugging its own code or prompts within a critical advice generation module to ensure the absolute accuracy and safety of the information it provides before showing it to a user. It really elevates the AI from just a reactive tool that answers questions to a more proactive, deeply analytical partner capable of navigating the kind of nuanced complexities that human experts grapple with daily.
That's a significant leap in capability. Okay, let's delve into the key reasoning techniques that allow agents to engage in this kind of internal monologue or structured thinking. First up, probably the most well-known, chain of thought, or COKI, prompting. My understanding is this is like explicitly asking the LLM to think step by step or show its work. Instead of just giving the final answer, it generates a sequence of intermediate reasoning steps leading up to it.
That's a perfect description. Ch15 is incredibly powerful because it forces the model to break down complex problems into smaller, more manageable subproblems. This has been shown to significantly improve performance on multi-step reasoning tasks like arithmetic, common sense reasoning, or planning problems. But perhaps just as importantly, the real insight of Ch15 is that it externalizes the model's internal thought process. It makes the agent's reasoning transparent.
And why is that transparency so important?
It's crucial for building trust and enabling oversight, especially for autonomous agents that might take actions based on their reasoning. If you can see how the agent arrived at an answer or a decision, you can audit it, debug it, and have more confidence in its reliability. The example of the information retrieval agent in the source material clearly demonstrates this. You see the agent's explicit thought process. First, analyzing the user query, then formulating specific search queries, next, maybe simulating or planning the retrieval, then synthesizing the retrieved information, and finally, reviewing and refining the answer. That whole agent's thought process section is the literal chain of thought, showing each deliberate step.
So how might that look in the crisis response context?
An agent assisting a crisis responder could use Ch15 to structure its analysis of a complex scenario presented by a survivor. Its internal monologue, exposed perhaps to the human responder, might look like: 1. Initial assessment. Identify immediate safety risks based on keywords, threatened, weapon mentioned, and user history. Priority: high. 2. Resource identification. Based on location and stated needs, shelter, legal advice, query the resource agent for available options matching criteria XYZ. A2. Communication strategy. User seems highly distressed. Formulate response using empathetic language, present options clearly, prioritize immediate safety actions. 4. Follow-up plan. Suggest secure check-in schedule, offer connection to specialized counseling agent, provide emergency contact info again. This structured step-by-step approach ensures thoroughness, reduces the chance of overlooking critical details, and provides a more comprehensive and safer pathway for support. The transparency also helps the human responder validate the AI's plan.
That makes the AI's process much clearer and verifiable. Now, building on chain of thought, the source mentions tree of thought, or Ch15. How does this differ? It sounds that it allows exploring multiple paths.
Exactly. While Ch15 typically follows a single linear chain of reasoning steps, Ch15 allows the LLM to explore multiple reasoning paths concurrently. It branches out, considering different intermediate steps or possibilities, like exploring different branches of a decision tree.
So it's not just one path, but several potential paths investigated in parallel.
Sort of. The model generates multiple potential thoughts or next steps at each stage, evaluates them, perhaps using self-critique or heuristics, and decides which paths to explore further and which to prune. This significantly enhances the model's ability to handle complex problem solving because it enables more sophisticated backtracking and self-correction. If one line of reasoning hits a dead end or seems unpromising, the agent can backtrack and explore an alternative branch it considered earlier. This is vital for tasks requiring strategic planning, creative problem solving, or complex decision-making where a single linear path might not be optimal or could easily lead to a suboptimal solution. It's about giving the agent the ability to explore solution space more broadly and intelligently, much like a human trying different approaches to a difficult puzzle.
That sounds much more flexible for complex, open-ended problems. And speaking of self-correction, that's our next technique listed explicitly. Self-correction, sometimes called self-refinement. This is about an agent internally evaluating its own generated content or thought processes to identify ambiguities, gaps, inaccuracies, or areas for improvement. It's like an iterative loop of drafting, reviewing, and refining.
Precisely. It directly integrates a quality control mechanism into the agent's generation workflow. The agent produces an initial draft or plan, then critically reflects on it against certain criteria or instructions, identifies flaws, and generates a revised, improved version. This loop can repeat multiple times. The example from the source, where a self-correction agent revises a draft social media post against the original requirements, vividly illustrates this. The agent analyzes its first draft, identifies weaknesses, lacks strong call to action, tone is a bit flat, proposes specific improvements, add question to engage users, use more active verbs, include relevant emojis, and then generates a revised, polished output.
That seems incredibly valuable, especially for critical output.
Invaluable. For critical AI outputs in a crisis response, setting things like summaries of legal rights, personalized safety plans, or drafts of communication to external agencies, a self-correction mechanism adds a vital layer of quality assurance. An agent could draft a safety plan, then internally review it against criteria like Is this plan clear and understandable for a user experiencing distress? Does it include all relevant local resources identified earlier? Does it adhere to established safety planning best practices and protocols? It could then identify gaps or confusing language and refine the plan before presenting it to the user or a human supervisor. This builds trust by making the AI's output significantly more reliable and tailored.
Okay, moving on. The next technique is Program-Aided Language Models, or PALMs. This sounds interesting, combining LLMs with actual code execution.
Yes, PALMs leverage the strengths of both worlds. They combine the natural language understanding and generation capabilities of LLMs with the precision and deterministic nature of symbolic reasoning, typically by allowing the agent to generate and execute code, often Python.
So if the agent needs to do some complex math or manipulate data in a very specific way,
Instead of trying, and potentially failing, to do it purely within the LLM's fuzzy, probabilistic reasoning, it generates a small snippet of code to perform that precise task. It then executes that code, often in a sandboxed interpreter, gets the exact result, and feeds that result back into its language model to continue the reasoning process or formulate the final natural language answer.
so it offloads the tricky, precise bits to code.
Exactly. It offloads tasks requiring high-fidelity calculation or structured data manipulation to a deterministic programming environment. The example from the source, showing a root agent leveraging a specialized search agent, which might use APIs, and a code agent, which executes Python, demonstrates how an LLM can orchestrate the use of specific tools for tasks like web search and code execution as part of its reasoning. This hybrid approach significantly increases reliability and accuracy for tasks where LLMs alone might struggle with precision, making agents more robust and capable of handling complex, factual, or quantitative inquiries. It's about combining the LLM's broad understanding with the deterministic power of code.
That makes a lot of sense. Use the right tool for the job. Now, the source mentions something more advanced, reinforcement learning with verifiable rewards, or RLVR. How does this fit in?
RLVR tackles a limitation of basic chain of thought. Standard code often produces a fixed-length reasoning chain. RLVR enables a more dynamic approach. It involves training specialized reasoning models that learn to dedicate a variable amount of computational effort, essentially, thinking time, depending on the perceived difficulty of the problem. This allows them to produce longer, more dynamic chains of thought when needed, enabling complex behaviors like iterative self-correction and backtracking within the reasoning process itself. They can spend more steps refining their thoughts on harder problems. RLVR is the training strategy used to achieve this. Models are trained using reinforcement learning on problems where the correct answer or a verifiable outcome is known. The model gets rewarded for reasoning trajectories that lead to the correct answer. This process helps the model learn effective reasoning policies, strategies for planning, monitoring its own progress, evaluating intermediate steps, and deciding when to backtrack or refine. It ultimately builds more autonomous AI agents that can adapt their reasoning depth dynamically to the complexity of the task at hand.
So it learns how to think effectively, not just follow a fixed script. Very interesting. Next up is React, which stands for Reasoning and Acting. You mentioned this earlier. It integrates Code Lady with the agent's ability to interact with external environments through tools. It's that iterative loop: thought, action, observation, thought. This sounds like a really practical way for an agent to operate in the real world.
It is extremely practical and powerful. React provides a framework for agents that need to not just think, but also do things in an environment and learn from the results. The cycle is key. 1. Thought. The agent reasons about its current state, its goal, and what action would be most useful next. This is like an internal code step. 2. Action. Based on the thought, the agent selects and executes a specific action, usually by calling a tool. For example, query a database, search shelters, like location 6 away, use a calculator calculated distance, call another agent via A2A. 3. Observation. The agent receives the result or outcome of its action from the environment or tool. AG, database, returns 3 shelters, details attached. Calculation result is 15.7 miles, A2A response received. 4. Thought. The agent incorporates this new observation into its internal state and reasons again, planning the next action based on the updated situation. This iterative loop allows the agent to dynamically adapt its plan based on real-world feedback, correct errors if an action didn't produce the expected result, and achieve complex goals that require multiple interactions with a potentially unpredictable environment. It provides a much more robust and grounded problem-solving approach than just linear code because the agent is constantly checking its understanding against reality.
Let's apply that React loop to the crisis response agent again.
Okay. Imagine the agent needs to find immediate safe housing for a user. Thought. User reports immediate danger at current location, zip code 12345. Goal, find available shelter nearby urgently. Action, search local shelter database for zip 12345 with immediate availability. Action, execute search shelters, location 12345, immediate availability. True. Tool call. Observation, receives result. Shelter A, available 5 miles away. Shelter B, available, requires pre-screening call first, 8 miles away. Shelter C, full. Thought. Okay, Shelter A is an immediate option. Shelter B needs an extra step. Users in high distress, prioritize speed. Action, present Shelter A details clearly first. Mention Shelter B as a secondary option requiring a call. Also, check transport options. Action, formulates response to user. Maybe call a check transport destination Shelter A tool. And the loop continues. This iterative process ensures the agent is adaptive and responsive, directly reacting to the information it gathers from its environment, the tool results, in a structured, deliberate way.
That interaction with the environment seems key. Now, moving beyond a single AI's thought process, even a complex one, the source talks about collaborative reasoning. First, chain of debates, or COD. This involves multiple, diverse models collaborating and arguing to solve a problem, like an AI council meeting.
That's a great analogy. Instead of relying on a single agent's reasoning, even with COD or React, COD brings multiple AI agents, potentially with different strengths, architectures, or prompting strategies, together to tackle a problem collectively. They essentially critique each other's reasoning, present arguments and counter-arguments, and debate potential solutions. This framework, proposed initially by researchers at Microsoft, aims to significantly enhance accuracy, reduce the impact of individual model biases, and improve the overall quality and robustness of the final answer by leveraging collective intelligence.
So it's like AI peer review in real time.
Exactly. The process itself generates a transparent, trustworthy record of the debate: who argued what evidence was presented, where consensus was reached. The most profound shift here isn't just about getting a better answer through more steps, but about forcing the AI into an internal peer review process. This isn't just making it potentially smarter, it's pushing it towards being more trustworthy and auditable. It shifts from a solitary agent providing an answer to a collaborative team working together to find a more validated solution.
Taking that collaboration even further, there's graph of debates, or GUD. This reimagines the discussion not as a linear chain or even a simple back-and-forth debate, but as a dynamic, nonlinear network. Arguments are nodes, connected by edges like supports or refutes. It sounds complex, but maybe more realistic.
It is more complex, but it mirrors how complex human debates or research efforts often unfold. This graph structure allows new lines of inquiry or sub-arguments to dynamically branch off from the main points, evolve independently, perhaps explored by different specialist agents, and even merge back later if connections are found. A conclusion isn't necessarily reached at the end of a single sequence. Instead, the system identifies the most robust, well-supported clusters of arguments within the entire graph. Well-supported here means arguments grounded in verifiable knowledge, maybe established facts, factual evidence retrieved via search grounding, or points where multiple diverse models reached a consensus independently. This provides a more holistic and realistic model for complex, collaborative AI reasoning, allowing for much richer, more nuanced exploration of multifaceted problems where there might not be a single linear path to a solution. It's a powerful metaphor for how complex human teams, or even scientific fields, arrive at robust conclusions over time.
These collaborative reasoning methods sound powerful, but also incredibly complex to design and orchestrate manually. This leads perfectly into the next topic, MSS, or multi-agent system search. This aims to automate and optimize the very design of these multi-agent systems by interleaving prompt optimization and topology optimization. It sounds like it could take a lot of the guesswork out of building these intricate collaborations.
It really aims to do just that. MassS, developed by researchers, tackles the combinatorial explosion of choices you face when designing a multi-agent system. Which agents do you need? How should they interact? How should each be prompted? It's structured as a 3-stage optimization process designed to systematically search the vast design space and find high-performing configurations for a given task. The first stage is block-level prompt optimization. Before even thinking about how agents connect, MASS focuses on optimizing the prompts for individual types of agents in isolation. For example, it might fine-tune the prompt for a generic debater agent to make it act like an expert fact-checker for a major publication, to ensure it performs its intended role meticulously and effectively. Get the building blocks right first.
Great. Optimize the individual components. What's next?
The second stage is workflow topology optimization. Here, Amass explores different ways to connect these optimized agent blocks. It selects and arranges agent interactions from a predefined design space of possible workflows. Should agent A talk to B, then C, or should A talk to B and C in parallel and their results go to D? It uses a clever, influence-weighted search method to guide this exploration, focusing on combining agent types and interaction patterns that seem most promising based on early evaluations. For instance, for coding tasks, it might discover that a hybrid workflow combining iterative refinement by a predictor agent with verification by an executor agent yields the best results.
So it figures out the best way to wire the agents together.
Right. And the third and final stage is workflow-level prompt optimization. After the best topology, the wiring diagram, has been identified, MassS performs a final global optimization pass on the prompts for the entire system. This fine-tunes the prompts specifically for their role within that chosen orchestration, considering the interdependencies between agents. For example, it might refine a predictor agent's prompt with meta-knowledge about the overall workflow, or add high-stakes role-playing instructions relevant to the specific dataset being used, now that its context within the full system is known. Key findings from the research behind MassS highlight 3 practical principles for designers. First, optimize individual agents thoroughly. Second, focus on composing topologies that leverage influential agent roles effectively. Third, don't forget to optimize the interdependencies and communication between the agents in the final configuration.
How could MassS help with the complex crisis response system we've been discussing?
For that kind of complex, multifaceted system, MassS could be incredibly valuable. It could automatically explore and design the optimal interaction flow between, say, an intake agent, a legal information agent, a psychological first aid agent, and a safety planning agent. It would figure out the best topology, maybe the intake agent delegates to legal and safety in parallel, and their outputs feed into the psychological agent. Or maybe a sequential flow is better. Mass would search for the best structure. And crucially, it would also optimize the prompts for each agent within that specific structure, ensuring they communicate effectively and their individual contributions maximize the overall system's ability to provide effective, coordinated support and rapid response. This could free up human developers to focus more on the high-level goals and agent capabilities, rather than getting lost in the weeds of intricate system design and prompt tuning.
That sounds like a huge accelerator for building complex agent systems. Now, we often hear about scaling laws for training LLMs, bigger models trained on more data perform better. But the source highlights something different: the scaling inference law. This principle dictates that an LLM's performance predictably improves with increased computational resources during inference when it's actively generating an output. What's the significance of this?
This is a really important concept for practical deployment. The scaling inference law reveals that you can often get significantly superior results from a smaller, potentially cheaper LLM simply by intelligently augmenting its thinking budget at inference time.
So use a smaller model, but let it think harder or longer.
Exactly. For example, instead of just taking the first answer the model generates, greedy decoding, you could instruct it to generate multiple potential answers using techniques like self-consistency sampling, and then use another process, maybe even the same model in a critique step, to select the best one among them. Or you could employ techniques like chain of thought or tree of thought, which inherently require more computational steps during inference for the same input query compared to direct answering. This fundamentally challenges the common, sometimes naive assumption that bigger model is always better for deployment. The critical insight is that you can often achieve top-tier performance without needing the absolute largest, most expensive models, simply by getting smarter about how you leverage them during active use by increasing the inference time computation.
How does this help in practice?
It provides a crucial framework for making nuanced trade-offs between model size. Smaller models generally require less memory and storage, making them easier to deploy, especially on device. Response latency. Increased inference computation, more thinking steps, naturally adds latency. The scaling law helps understand this trade-off and find the sweet spot for your application's needs. Operational cost. More inference computation means higher cost per query, but if it allows you to use a significantly cheaper base model while achieving the same quality, it can lead to overall cost savings compared to just using the biggest model available.
So this means more nuanced and potentially much more economically viable approaches to AI deployment for you, the developer. It's about ensuring resources are allocated intelligently for maximum impact, rather than just blindly scaling up the base model size. It's about working smarter with the models you have, not just needing bigger ones.
Precisely. It empowers developers with more control over the performance cost curve.
Okay, finally, in this section on reasoning, let's talk about deep research. The source mentions applications like Perplexity AI, Google's Gemini research capabilities, and advanced functions in OpenAI models as examples of this. You give the AI a complex query and maybe a time budget, and it acts like a tireless, methodical research assistant.
Exactly. This represents a significant evolution from traditional web search. It fundamentally changes the interaction model from a simple query and retrieve list of links to a truly autonomous investigative process delegated to the AI. Instead of you sifting through search results, the AI does the heavy lifting. You give it a complex question or research topic, and instead of immediate links, you receive back a detailed, synthesized report, often complete with citations and summaries of sources.
How does it work under the hood? What steps does the AI take?
It typically performs a multi-step, iterative process autonomously. 1. Initial exploration. It breaks down the complex query into sub-questions and performs initial targeted searches using standard search engines or specialized databases. 2. Reasoning and refinement. It analyzes the results from the initial searches, identifies key information, but also spots gaps, inconsistencies, or contradictions between sources. 3. Follow-up inquiry. Based on its analysis, it formulates new, more nuanced search queries to fill the gaps, resolve contradictions, or explore promising leads it discovered. This iterative search and refine cycle is key. 4. Final synthesis. Once it determines it has gathered sufficient validated information, perhaps based on a time budget or convergence criteria, it compiles the findings into a cohesive, structured summary or report, often citing the sources it used. This is an incredible productivity booster for knowledge workers, researchers, or anyone needing to quickly get up to speed on a complex topic.
Is there code available to see how this kind of iterative research loop is built?
Yes. The source points to Google's open-sourced deep search code, which is part of the Gemini full-stack LangGraph Quick Start repository on GitHub. LangGraph is a great library for building these kinds of stateful, cyclical agent applications. The state graph code in that example clearly shows how different processing steps are defined as nodes, things like generate a query to formulate search terms, web research to execute the search, reflection to analyze results and decide if more research is needed, and finalize answer. Conditional edges then control the flow. For example, after web research, an edge like evaluator research might lead to the reflection node. The reflection node is particularly key as it makes a decision. Is the context sufficient for answering, or is more research needed? Based on its output, the graph either loops back to generate a query or proceeds to finalize answer. This explicitly implements that iterative research loop.
That's great. Developers can actually look at and adapt that LangGraph code. How could this deep research capability be applied in the crisis response scenario?
Imagine an AI agent assisting a paralegal or advocate within a domestic violence organization. They might ask it a complex legal question. What are the specific residency requirements and evidentiary standards for obtaining a long-term protective order in County X for a survivor who recently fled from County Y, considering recent case law Z? Instead of the humans spending hours searching legal databases and case law, they could delegate this to the deep research agent. The agent would autonomously perform the iterative search, analysis, and synthesis across relevant legal databases, statutes, and case law repositories. It could then provide back a comprehensive, accurate report summarizing the findings, highlighting key requirements, potential challenges, and citing the specific legal sources. This would free up the human staff for direct client interaction and strategic case planning, ensuring that the advice they give is grounded in accurate and up-to-date legal information, even for highly nuanced or cross-jurisdictional situations. It ensures precious human expertise is focused where it's most needed, supporting the survivor.
That's another really compelling use case. So after exploring all these techniques, COT, 2T, self-correction, POLEMs, ROVR, React, Code, God, MassS, scaling inference, deep research, what does it all mean for how an agent thinks? It's clearly not just a simple input-output black box anymore. It seems much more like a structured, often iterative process.
You're absolutely right. It's a structured approach that typically combines reasoning and acting. At its core, for many modern agent frameworks, it boils down to that thought-action-observation loop we discussed with React, powerfully driven by an underlying LLM. The thought phase is where the LLM generates that internal monologue planning, analyzing, breaking down the problem, maybe asking itself questions, often using techniques like co-type. Based on that thought, the agent selects and executes a discrete action action. Maybe it uses a tool to search the web, retrieve data from a vector store, call another agent via A2A, execute some code, or simply provide an answer to the user. Then it receives observation of feedback or result from the environment or tool based on its action. This observation feeds directly back into its internal state, triggering the next thought cycle. This cycle repeats think, act, observe, think, act, observe until the agent determines, based on its reasoning, that it has reached a final, satisfactory solution or achieved its goal. Often, few-shot learning, providing examples of good thought action sequences in the prompt, is used to guide the LLM's behavior within this loop. And the frequency or depth of the thoughts can be adjusted based on the task. You might want more frequent interleaved thoughts for complex fact-checking, or perhaps sparser, higher-level thoughts for strategic decision-making tasks. This makes the agent's internal process incredibly flexible and adaptable. Hashtag tag 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 outro.
Wow, okay. We have covered a lot of ground today. Seriously, deep dive. We went from getting AI agents to actually talk to each other reliably and securely, using A2A, enabling truly collaborative AI teams, to making those agents smart spenders of resources through dynamic routing, fallbacks, and other optimization techniques. And finally, diving really deep into how agents can think more profoundly, showing their work with chain of thought, exploring options with tree of thought, interacting with the world via React, and even engaging in collaborative reasoning with frameworks like chain of debates and God.
We really did. And for everyone listening, remember, you've already built powerful chatbots. You've mastered prompt engineering with single agents. That's a fantastic foundation. Now, by starting to integrate these agentic design patterns, A2A for communication, resource optimization for efficiency and resilience, advanced reasoning for depth, you're moving beyond creating tools that just respond. You're starting to build truly autonomous, adaptive, and resilient AI systems. These patterns are the pathway, the building blocks for developing solutions that can orchestrate complex, multi-step workflows, operate efficiently and reliably within real-world constraints, and reason through complex challenges with transparency and precision. And these qualities, orchestration, efficiency, resilience, reasoning, transparency, they're absolutely vital for effectively supporting organizations like domestic violence crisis response centers. In that context, every interaction, every piece of information, and every decision supported by AI can have a profound, real-world impact on a person's safety and well-being. It's about empowering those who work tirelessly to empower others.
Absolutely. Well said. This isn't just about technical advancement for its own sake. It's about enabling the creation of AI systems that can make a profound social impact safely and effectively. So, as we wrap up, the final provocative thought for you, our listener, reflecting on your own goals, perhaps in supporting critical services or tackling other complex challenges, what specific problems are you now eager to tackle with these new agentic patterns? And more importantly, how can the AI systems you build move beyond simply reacting to truly anticipating needs, adapting dynamically, and ultimately empowering those in need, making a tangible, positive difference in the real world?